Hi, this is Sally's Book Talk, bringing you the best books from around the world every day. Today we're introducing a science book about Einstein and relativity. Professor Harold Fritzsche's The Equation That Changed the World. When it comes to the world's most renowned physicist, it's undoubtedly Einstein. Einstein's greatest contribution was developing relativity theory and deriving the mass energy equivalence formula E equals mc squared. This forms the core content of the book we're discussing today. Before we dive in, let's learn about the author, Fritzsche. Fritzsche was a German theoretical physicist known for his sharp wit and courage. Back in 1968, as a student, he escaped from East Germany to West Germany. His true destination was Munich, where he sought mentorship from Professor Heisenberg, the founder of quantum mechanics, launching his scientific career. Fritz became an accomplished science writer whose works have been translated worldwide, influencing 2 generations. This book, The Equation That Changed the World, has won multiple awards, including the Wingen Book Award. Few books can explain special relativity as thoroughly as this classic science work does. Now let's explore the book's main content. The book features an imaginative structure, where Newton and Einstein time travel to meet Professor Haller, the author's avatar for scientific discussions. These 3 characters represent 3 physics eras: classical, modern, and contemporary, with Newton as student, Einstein as teacher, and Haller as teaching assistant. Like Newton in the book, we'll follow Einstein's thought process. Let's explore how E equals mc changed our world. The 250,000-word book contains 21 chapters. We'll divide the content into 2 parts. 1. What is the equation? 2. How did it change the world? First, we'll address 3 questions. 1. The equation's origin. 2. Basic ideas of special relativity. 3. Information encoded in the equation. Let's start with the first question. How was the mass energy equation born? Great theories are usually born to solve specific problems. Let's examine what problem emerged. In high school physics, we learn about the principle of relativity, one of Newtonian mechanics' core concepts. It means if you're standing on a moving subway, you're stationary relative to the train, but moving relative to the platform. Motion depends on reference frames. Following this theory, electromagnetic wave speed shouldn't be an exception. In 1864, British scientist Maxwell proposed a electromagnetic theory requiring equal light speed propagation in all directions through vacuum. Initially theoretical, it later sparked technological revolutions. Microwave ovens were invented based on this, and broadcasting uses electromagnetic waves. Scientists then faced reconciling relativity principle with electromagnetic theory. Einstein revolutionized physics by abandoning absolute space, proposing relative space-time concepts through his 1905 special relativity theory, deriving E equals mc. This leads to our second inquiry. What's the fundamental concept of special relativity? Unlike Newton, Einstein believed different reference frames have relative time and space. Their interplay forms space-time concept. For example, standing still in absolute space means motion through time in relativity's framework. When running, part of time travel motion converts to spatial movement. your time-traveling speed slows down. If you could run mere light speed, congratulations, you'd stay youthful. This time, dilation isn't noticeable daily, as we move much slower than light. From this perspective, life lies in movement. Makes perfect sense. Let's discuss the fundamental principles behind special relativity. 2 core principles. First, relativity principle. Physical laws remain consistent across all reference frames. Second, light speed constancy. In all reference frames, light speed in vacuum remains unchanged. Whether light source is stationary on ground or moving at high speed, light speed remains constant. Using these principles, Einstein derived E equals mc, energy equals mass multiplied by light speed squared. What makes this equation revolutionary? Previously separate concepts, time, space, and mass, energy became interconnected. This equation fundamentally challenged Newtonian mechanics' traditional views. Like most physicists, time-traveling Newton in the book struggled to accept Einstein's radical space-time concept. Einstein and assistant Haller patiently guided Newton through these concepts. Einstein once used an analogy to explain relativity. When Einstein was a renowned professor at Princeton's Institute for Advanced Study, his secretary requested a simple explanation for journalists. The genius replied, "Like a modern meme creator, an hour with a pretty girl feels like a minute, but a minute on hot stove feels like an hour." The stove represents high speed, reference frame, where time perception changes. Within such frames, time appears to slow down. Many challenged special relativity. French physicist Paul Langevin proposed twin paradox in 1911. This experiment imagines twin brothers. One stays on Earth, the other travels space at near light speed. When the space-traveling twin returns age 2, his earthbound sibling would have died centuries ago. Doesn't this sound like the Chinese legend where a day in heaven equals a year on Earth? Challengers like Langevin ultimately helped popularize special relativity. If relativity still puzzles you, visit the Beijing Electron-Positron Colb at the Institute of High Energy Physics. This high-energy accelerator has operated for over 2 decades. It accelerates electrons and positrons to near light speed before making them collide head-on. The collision results in complete annihilation of both particles. But we learned in school that matter can't be destroyed. Where does their mass go? The answer: mass converts to energy, which then forms new particles. Precisely what E equals mc describes. Now let's answer the third question. What information does E equals mc reveal? E equals mc squared. 3 crucial insights emerge from this equation. First, mass and energy are fundamentally equivalent. Mass is stationary energy, energy is moving mass. Second, light speed plays a unique role in this equivalence, the universe's most remarkable constant. Third, it reflects Einstein's pursuit of fundamental connections and mathematical elegance. Understanding E equals mc leads us to its world-changing impacts. These changes range from daily applications like GPS and nuclear power to jolt shifts through nuclear weapons development. Let's examine 3 areas: GPS systems, nuclear fission, and fusion energy. First, GP's navigation relies on relativity. Modern life increasingly depends on GP's technology. Its functioning requires relativity adjustments. Satellites' faster speed makes their clocks run slower. Maintaining precise clock synchronization between GPS satellites and ground stations requires relativistic corrections. When calibrating space and ground clocks, Einstein's special relativity becomes essential. Without relativity adjustments, daily positioning errors would render GPS unusable. Second, heavy nuclear fission initiated the atomic age. A typical reaction involves uranium-235 absorbing neutrons to become uranium-236. Uranium-236 fission releases lighter nuclei and massive electromagnetic energy. Fission requires reaching critical mass, about 50 kilograms of uranium-235. 1 kilogram of uranium releases 80 trillion joules, equivalent to burning 27,000 tons of coal. Nuclear power offers super-efficient clean energy through controlled fission. Unlike atomic bombs, reactors allow safe shutdown during malfunctions. Nuclear energy revolutionized both technology and global politics. The 1945 atomic bombings of Hiroshima and Nagasaki killed over 100,000, accelerating WWII's end. As Fritsch noted, most bomb-creating scientists only endorsed desert demonstrations. While scientists built the bomb, politicians decided its use. Einstein expressed anguish in a 1950 letter. I never conducted research for bomb development. My sole contribution was establishing mass-energy equivalence in 1905 pure physics with no military intent. Third, through hydrogen nuclear fusion, humanity might create a second sun. Nuclear fusion involves light atomic nuclei colliding and merging under extreme heat and pressure. Crucially, this requires temperatures exceeding 100 million degrees. During this process, escaping neutrons release tremendous energy, the power source of stellar radiation. As early as 1940, scientists recognized solar fusion converts mass to energy via Einstein's equation and Fermi's theories, enabling Earth's life-sustaining warmth. This same fusion energy drives hydrogen bombs' devastating power. Fusion releases vastly more energy than fission. A hydrogen bomb's flash could be seen from the moon. Controlled fusion could provide limitless clean energy, essentially creating an artificial sun. Though this artificial sun remains distant from practical implementation. Even if controlled, recreating fusion's extreme conditions proves immensely challenging. Scientific progress defies strict timelines. Fusion may become viable as civilization advances. Abundant energy carries risks. History shows societies tend toward reckless consumption. As Haller states, prudent energy use enables sustainable human civilization. E=mc reveals mass energy conversion, enabling nuclear plants, weapons, and cosmic transformations. This fundamental process gives us sunlight and life itself. Now, understanding relativity better, we appreciate Einstein's extraordinary brilliance. For over a century, physicists have worked to validate Einstein's theories, including the 2017 Nobel Prize in Physics, awarded to the gravitational wave detection team. Notably, Einstein developed these theories through pure imagination, without financial resources. Let's address two additional interesting questions. 1. Why was Einstein, rather than others, able to establish special relativity? The reason lies in Einstein's profound understanding of light's nature. Einstein's first 1905 paper discussed light quanta, photons. This work earned him the 1921 Nobel Prize. Massless photons must travel at constant speed, defining cosmic speed limits and special relativity's foundation. 2. How did Einstein discover physical laws with such simplicity and depth? Scientific elegance permeated Einstein's work, exemplified by his 1915 general relativity equations. Their mathematical form remains remarkably simple. In a 1932 Columbia University lecture, he emphasized seeking the simplest possible system, unifying observations. Simplicity meant minimal, independent assumptions, not ease of learning. This explains Einstein's unification of time-space and mass-energy concepts. Simplicity indeed marks truth's signature. Fritz concludes the book at CERN, near Geneva. Facing humanity's largest scientific instruments, Newton and Einstein become eager students. After Haller explains E equals mc's manifestation in particle accelerators, our relativity journey concludes. E equals mc squared. This magical equation reveals the essential equivalence between mass and energy, enabling their mutual transformation. Our world fundamentally operates according to this equation. Building upon E equals mc, humanity developed GPS, nuclear plants, and atomic weapons, fundamentally altering our world's trajectory. That concludes our exploration. Find keynotes below the audio. See you tomorrow.